Hello everyone. In this lecture, I'll be explaining how to factorize an integer and how to find the prime numbers in some given range. So I begin with the integer factorization. So as we mentioned earlier in the fundamental theorem of arithmetic, that we can factorize any integer n to a set of unique prime numbers. So in this, for the set and the counts of the primes will always be unique. So for example, here if we have 30, this is factorized 2 by 1, 3 by 1, 5 by 1. And if we have 1, this factorized 3 by 1, 17 by 1. We have something like 90. So this is 2 by 1, 2 by 2, and then 5 by 1. That's it. So these are some examples for the factorizations of some numbers. So how do we find that? So there are like two ways, but one of them is very naive. You can remove that. I will begin by showing it in code right away. So the naive way is to go through all the numbers from 2 until the number n that we'd like to factorize. And we never see that n is divisible by p. And when this is true, we keep dividing by p. Count the exponent. So here you can see that the factorization goes through from all p from 2 until n. Here we keep, this is the exponent, we keep increasing it. And here so whenever n is divisible by p, we keep dividing by p, and we add this e. So we are counting the exponents and until we can't divide by p anymore. And here, if there was any p, we'll just print. For example, here rise 90. As you can see here are the exponents. So the very naive way has a prime complexity of n, which is, I think, yeah, it's very big. So we'd like to move to a bit better algorithm. So here we will depend on some observation, basically that if we have an integer n, and we can write it as a product of two numbers, we assume without loss of generality that a is greater than or equal to b. So we can't have that b is greater than square root of because if this is true, this would imply that also a is greater than the square root of n, and that a implies that a times b is greater than n, which is wrong. So because of this, we have the contradiction. So we'll say that b is smaller than or equal to the square root. Otherwise, so we can only have one number, which is a, that it is greater than the square root. So if we look at the prime divisors, it has to be also the same. So it's only one exponent, one prime exponent, so n is equal to 1, 1, n again. Assuming that the primes are sorted. So if we take this part, as the a, then this will be the b. Sorry, this is the b. So this is the a. So this has to be the less than the square root. It doesn't have to be always like that. It depends on how we order the primes. Because here we could have like this part is really big, and it's much bigger than this. Example like here, like 1. But in that case, there are any number in this that is greater than the square root of this product. So the point here is, no matter how we reorder the factors, we can only have at most one factor that is greater than the square root. And so here, if we take, for example, the Pn, so one of them is the A, and the remaining are B. So you might still find the right order. So yeah. Okay, so going from this observation, I'll explain the other algorithm. So the other algorithm will go instead from 2 to n, it will go only from 2 until the square root. Right, square right. Here I like to do it like that. It's p times p is then equal to n, instead of using the square root function and getting the floating point numbers, which are usually a bit problematic to deal with. To do that, but it might happen in that case that the m still has some remaining divisor, which is basically the one that is greater than the square root. So in that case, we need to check for it, check if there's still remaining divisors. can add an asterisk statement. Check that the number is 1 after divisor. This is the old factorization. Now we use the new one. So it gets exactly the same result. And here, since we have this assertion, so we guarantee that the number is factorized because we took all of its factors out. If you notice that here we always find the prime divisors, because once we reach a divisor here from this loop, so once we reach some certain t, means we have gone through all the numbers from 2 until t minus 1. And if any of those was a divisor of p, then we already factored it out while factorizing using one of these smaller numbers. So it means that the n wouldn't be divisible by p anymore. For example, if we have like the for the p, let's say the p became 7. And n originally was 420. For this, we kept devising because this was the original number. So when we go by equal to, we keep dividing here by 2's. So we get 110 and then 105, and that's it. So we find like two. So the exponent of 2 is 2. Then we divide this number by 3. This should be, yeah, it will be 35. So after we divide the 105 by 3 is 35, and by 5, then divide it 7. So as you can see, before we reach that t is equal to 7, we already took all the factors that are less than 7. So if the number was divisible by 2 or 3 or 4 or 5 or 6, then it's already taken away. You can see it here that here the t was equal to 6. But here we actually didn't do anything because like the t, like the 6 is already factorized as 2 and 3. And we already, before we reached the 6, we already took all the powers of the 2 and the powers of 3 out. So the number until here is already not divisible by 6. So yeah, and the same applies. So whenever we reach that there's a number here that is divisible by p, then this p is a prime. As you can see here. So this is why this algorithm finds the prime factors. Let's see this that we have done. So this was the integral factorization. I'll get to the sieve after that. The sieve operates, so we have the numbers to so if we have all these numbers from 2 until 26, we'd like to find out which of those are primes and which are not. So we begin by all as marked as being prime. So we assume that every number is a prime in the beginning. Then we go through the numbers in a loop. So here we find the 2. So we find that it is a prime. We'll go through all its multiples and unmark them as a prime. So they will be marked as not prime. So here we go, 4, 6. All of these will be unmarked because they're all multiples of 2. So they're not prime. And then we go now the 3 and go through all its multiples, mark them. And so on. And then the 5 we go through its multiples. And then the 11 go, sorry, the 7 will go through its multiples. And then the 11 go through its multiples, and then we will do nothing. So this is the sieve. So to report at the end that the prime numbers that we have are 2, 3, 5, 7, 11, 15, 17, 19, and 23. You can also go by using the multiples of 4, for example, but it's actually useless because we already all the multiples of 4 are unmarked because they are multiples of 2. So that's why it's more efficient to check if the number is prime or not before we go for its multiples. It's not necessary for the correctness. So you can write that in code. Here you can see this is the inner loop of going through the multiples. So start with the multiple at 2 times p, or equivalently p plus p, and we move with the step p. Here we unmark p. It's not a prime anymore. And go to 0. So next one. And check if the number is prime, and it's empty. So this is the code that makes the sieve. So we can call it and see the result. So as you can see here are the prime numbers until 30. Here we can make some optimization. As you can see, we can find here that there are numbers like this, this, and this. So they are like marked multiple times because they have more multiple. So we can reduce the effect of this by going through the numbers. So if we have the so here we go from 2p until as much as we can. We will go from 2p, 3p, and 4p, and then until p minus 1 times p, and there's p times p, this is squared, then p plus 1 times p, and so on. So all these numbers here until before p square, we don't actually have to go through them because they already got unmarked, because this one is a multiple of 2, which is before the p. So this we don't have to do, and this is a multiple of 3, which is already unmarked, this and this. So all of these are already unmarked. So the number that we are not sure if it's marked, it's the p squared. So this is where we have to start. Actually, the p squared exactly won't be marked. So this here we can make by changing this part here and make it like that. So it still gets the same result. So basically this is the sieve in general. So I'd like to go through the time complexity of it. So the first thing, I will assume that we don't actually check if the number is prime, and we also go through without this first optimization that I mentioned. So it's like that, so it still gets the same result. So what is the time complexity here? So here we have so this inner loop makes like max prime over p steps. So as you can see, we go p, 3p, 4p, and so on, until n over p. So this is a flooring after we divide m by p. So we notice that if we increase this number by 1, then for sure this product will be greater than m. So that's why we stop here. So basically here we do in the inner loop m over p minus 2 plus 1 iterations. So m over p minus 1. And then we make the summation of this to the sorry, the p is 2 and 3. Uh, so this we can find its upper bound by this. So if we remove the floor, we get slightly bigger value. Doesn't change the correctness, or it doesn't change the asymptotic value of this expression. So we get this value, and then we sum this. So this is like it's called the harmonic series. This part, like if we take 1/2 plus 1/3 until the 1/n. This is actually less than the natural logarithm. It could be +1 or something, but just a constant. I don't remember the exact value, but it was something like that. So here the log is the natural logarithm. Here it is the limit. That's that. So here we have this expression goes to the limit. And so this was a cone factor outside, so now it's here. Basically, without this optimization, here, like checking if the number is prime, and this, we would have like an m log n complexity. And I I wanted to make sure that we analyze this complexity, this part exactly, because it will be useful for other algorithms later on. So when we include this part here, as far as I know, this reduces the complexity a bit, but so it becomes m ln of m. Uh, so this complexity it has to do with the density of the prime numbers. That's why it's like that, because we only go of the multiples of the prime numbers. But still, I don't know exactly how this is proven. It belongs to some analytic properties of the prime function. I'll not get into that here. And also, maybe a good inequality to mention that we have the number of prime numbers until n. So it's given this symbol, so pi of n, and this is bounded by like n log base 2 n log base 4. So basically, this gives like a bound for the density of the prime numbers from 1 until n. So we can have an estimate how many numbers we need. For example, we want to have like all the prime numbers until 10 to the 6. So we want to know how many, for example, the size of the array for the prime flags we should have. So, or basically the count of prime numbers until 10 to the 6, we can use this formula to make sure. So it would be 10 to the 6 And here 10 to the 6 is kind of close to 2 to the power 20, so it would be something like that. So this would be near 50,000. A bit more, a bit less. Can make sure about that. But, um, it's actually this number. So yeah, I actually should have multiplied by 2 because this is the lower limit and we should have taken the upper limit. So it will be, so this the upper bound that we should get. You know, yeah, so, basic, so this value is twice as this value. So this was the sieve. We can have some other variants of the sieve. So instead of calculating if a number is prime or not, you can mark the smallest divisor in the number, for example. So here we can do this. We have all the number. Let's say not for this. This in bit bluish is the smallest divisor we have so far for the number. So here we begin, like also uh, in the same idea like the sieve. So we start with this, and we go through its multiple. So here we go to 4. So we remove this as smallest divisor and we'll put the 2. We'll put the 2, 2, and so on. So we mark all its multiples as having smallest divisor 2. Uh, then we go from 3. We start from 3 squared. So here we mark this 3, and we keep going with the stuff. Here we find that there's already a smaller divisor, so we don't do anything. Here we mark 3, we don't do anything. Okay. 3. And the 5, we go 5 square, we won't do anything, and basically we won't change anything. So we end up having some array like this. So it's saying the smallest divisor of 11 is 11, and 12 is 2, and so on. And here the interesting pattern to see is that like if some number is prime, we end up having the smallest divisor of this prime. This number is the number itself, which is part of the definition of the prime numbers. This was the old version of the sieve. So here we have this array that's called the smallest factor instead of this flag that we want to change. And here, instead of putting the initial values true, we just put the numbers themselves. And here to check a number's primes, to check if it's the smallest factor of itself. You will say the smallest factor is the minimum between the smallest factor we found so far and p. Here we go for the smallest. I forgot to include the so now we run this. Basically it prints the way we're expecting. So the smallest 2 is 2, the smallest 3 is 3, and so on. The smallest 7 is 7. And as we expect also for the prime numbers, we have the numbers themselves. This array can actually be very useful to factorize a given number. So we can always get the smallest prime divisor of some number, and we keep while we can divide. Different p. Here, instead of trying used to do factorization, is to try every possible p as a divisor. Now here we already know one divisor, so we can guess it right away. We don't have to actually guess to going through a lot of different numbers and try if it's a prime or not. Now here we already know, so we just get the smallest one. So here we have that, and basically we can factorize the rest. You can factorize the 90. Yeah, I know why it didn't work. So it wasn't working because we only processed the smallest factors until 31. Have actually need until more than 90. Here we still get the same factorization. So know that the 90 has smallest divisor to be 2. And then it's from the remaining numbers 3 and then 5 and so on. So basically this is what we have. So this is another way to factorize. So if we know that all the numbers we want to factorize are less than some number like 1 million or something, then we can pre-compute all the smallest factors, and then we can factorize really fast whenever we need to. So this factorization here, it happens in for, let's say log n, could be even less. So the naive one, the first factorization was taking off n operations. So here plus basically it's the number of times the inner loop got executed. So it's the sum of exponents, which is at most log n. So this is an upper bound. And for the other, so the one with the square root optimization, so this makes NO square root of n plus also log n. So this is the square root optimization, and so this last one, with the smallest factor, it's I'm sorry, the connection somehow stopped. as we said here. So this is for root plus the log of n. So this log n is amortized over all the loops, the n loops. So here we have with the smallest factor, this is of log n. These are the query times. Or the pre-computation. This here is, we don't do any computation. So this also is O1, O1. And here this is ON log n. Or n log n. It doesn't matter that much. I would say it's like log n. So this is the pre-computation time. So here we have to make sure that we pre-computed something for all the primes, and then we factorize really fast. But here, if we want to factorize just a few times, then we could use these ones. But if we want to factorize many times, so we can make this pre-computation and do this. We can also make use of this extension in order to compute some other, let's say, number theoretic functions. So if you would like to count the number of divisors for some number or the sum of its divisors, this we can all make in the same fashion. Again, the sum of divisors is 0. We don't have any divisors yet. In this case, we will begin with is equal to 1, because we would like to include 1 as a divisor. And we will basically just go through the multiples of p. Here, so here I'll start with the first multiple as p itself and not 2p, because we'd like to include the multiple. So we'd like to include the numbers as divisors of themselves. So I'll get to that. Here we work with the distance p. Say the sum of divisors of q, we just add q. And here we can say the number of divisors. And even say the product of divisors. This we have to make it like modulo some prime, because it can get really big. So just make that. Here is the number of divisors. Plus the product of divisor. So we print the sum of divisors and the number of divisors in the product. So here we get the table of the sum of divisors, a number of divisors and product of divisors. Actually, product should have started with 1, which is the empty product. Example, the 5 has the divisors 5 and 1, so the sum is equal to 6, and the number of them is 2, and the product is 5. The 6 has so the sum of divisors, so they are 1 and 2 and 3 and 6, so they sum up to 12. And the number of divisors here are 4, and the product is 6 times 6, so it's 26. And so on. So we can find here, so the sum of divisors, number of divisors, product of divisors, those all here. So I hope this part is clear. So it's coming from the same pattern that we go through all the divisors. And since we know a divisor and its, so since we know a number and its divisor, so we can include any information that we want. So here we from this divisor, or just add 1 that we counted in the divisor. Here we can, if you want to make, for example, the count of proper divisors. So the divisors without the number itself. So we don't count 6 as a divisor of 6. So here we don't start from the number itself, we start from the next divisor. This should be the 6. So here we find that the 6 has the sum of the numbers 1, 2, and 3. All the prime divisors have the sum, the prime numbers have sum of divisors to be equal to 1. You can see here, because there's only one this divisor. And here all the numbers counting divisors to be 1 are the prime numbers, and so on. So here we don't count the number itself as prime, or as one of the divisors, or we don't include the sum of divisors. So basically this happened here because when we want to make us by the multiple of p, make sure it's a proper multiple. So when we didn't have this here, we could have also the p is a multiple of itself, which would also make p as divisor of itself. But here, if we do this, so here we don't go to p as a multiple. So we don't find q as a multiple of p. P is a multiple of q, and so here we're not including the p as the divisor So here we are just using the proper divisor. We don't include the p itself. So I hope this part's clear. You can send me if you have any questions. So basically this was the sieve and the factorization. So yeah, and for the factorization, there are other algorithms that could do it. So there's it's on the like the polar draw. So this algorithm tries to somehow guess kind of randomly some divisor of a given number, and once we guess a correct divisor, so we can just divide by it as much as we can until we are left with a number and then two numbers, and then we have to factorize each of them again, and so on. We find an explanation of it in the Coleman book. Yes, it's- if I remember correctly, I think it's solved in this function, but I'm not sure. Uh, so yeah, and that's still an open field. It's a really hard problem to solve. Anyway. So that was it. I hope it was beneficial, and you can send me if you have anything. Thank you.